We're going to start with the device which we talked about last time. And this is a capacitor. And in this device, there are two plates. And on this plate, there are positive charges, and on this plate, there are negative charges. Now in this chapter, we're going to look at the motion of charges inside conductors. And we're going to talk about it as if it's the positive charges that move. That will be our model of conduction. The positive charges at this plate would love to go to this plate where the negative charges are. They would love to do that, but they can't because they're separated by air. But if we connect a conductor between this terminal and this terminal, charges can flow. And a conductor that we can connect between the two terminals is a light bulb. And inside the light bulb, there's a little tiny wire. And if I hook one terminal of the light bulb here, and I hook the second terminal of the light bulb here, here's what happens. The light bulb lights. And it's lighting because charges are going through the wire inside the light bulb. And in fact, we can use the brightness of the light bulb as a measure of how much current is flowing. Now, we're going to take a look at this device right here. This device will help us visualize the motion of charges. So there's dots inside here which represent charges inside the wire. So I'm going to hook up this side right here to the positive terminal of the capacitor. Charge will go here, through here, into this wire, into the light bulb, and then back into the negative terminal of this capacitor. And then what happens is this. The light bulb lights, and I want to visualize it this way. The light bulb is lighting because of the motion of charges. But as time goes on, you can notice something happening. The motion is slowing down. The charges are not moving as quickly, and the light bulb is getting dim. We need some way to quantitatively express this, and we'll do this using the concept of current. Current is the flow of charge. And in the book, we have an equation that defines the flow of charge as charge divided by time. So we imagine sitting at one place in a circuit and watching the number of charges that pass that point in the circuit in a given interval of time. That's what's defined as the current. And what's happening is, in each interval of time, there are fewer charges passing this point, and so there is less current passing that point. And because there's less current, the light bulb is less bright. Now I'm going to take this capacitor and I'm going to charge it back up again. And the way I'm going to charge it is just by connecting it to a generator. So I'm going to charge it back up, and I'm going to put charges back into the capacitor, and you can see now the motion of charges is going the other direction. I'm putting charges back into the capacitor, and as I do that, we say I am charging it up, and I am literally charging it up. I'm putting charges into it. That separation of charges inside the capacitor stores energy. And so I'm not only separating charges, I'm storing energy, and when I'm done with that, I've got energy, I have charges stored inside the capacitor, and I can light a light bulb. But I'm going to do something different. This time, I'm going to light not one light bulb, I'm going to light two. So I'm going to connect the terminal of the capacitor to the current device. The other terminal gets connected to a light bulb. And then this terminal of the capacitor is going to get hooked to the other side. And when I hook it here, I'll have a complete circuit. Now there's two light bulbs, which we'll call bulb 1 and bulb 2. Question, which bulb is brighter, bulb 1 or bulb 2? We'll give you some choices. Now current is the flow of charge. And charge is conserved. You can't create it, you can't destroy it. So any charge that goes through the first bulb has to keep on going and go through the second bulb. And so the current in the first bulb is equal to the current in the second bulb. And so in fact what we see is this. Both bulbs are equally bright.